In this chapter, Introduction to Inference, we're finally starting to get to the point of all the statistics that we've been working with. We learned how to calculate all those summary statistics, we learned to look at graphs, but this is really the main idea of what we want to get to in statistics is inference. And the whole idea of inference is taking something about a sample and inferring about it to a population. So for this chapter, we're going to be looking at uncertainty and confidence. We'll learn how to build confidence intervals. And then once we have a confidence interval, a general form for them, we'll talk about confidence intervals for normal populations when sigma is known. We'll look at tests of significance, and along with the tests of significance, we'll look at null and alternative hypotheses that we're interested in testing. We're going to be looking at two different types of tests of significance. We'll be looking at the traditional approach and the p-value approach, and then we'll be looking at tests of significance, again, where sigma is known. So to get started, I think a good idea is to talk about what inference is. So inference is basically talking about taking a sample and based on this sample inferring something about a population, because we can't find out all the information there is about a population. So again, inference is taking a sample and drawing a conclusion from this sample to the population from what that sample was taken from. So that's a good thing to know for a test. What is inference? Now, because we're working with samples, we have to introduce the idea of some uncertainty in the sample, because we know not every single sample that we take will be representative of the population. So the next thing we want to look at is uncertainty and confidence. Now, of course, the larger the sample size, the more confident you are that it's representative of the sample. So if you pick different samples from a population, you would probably get different sample means every single time, and virtually none of them would actually equal the true population mean mu. So that's a little bit disconcerting, because that's the whole idea of what we're trying to work with here. There, get to that to be readable. So again, if you pick different samples from a population, you would get different sample means, and virtually none of them would actually equal the true population mean. But what we hope is, if we take these samples over and over again, and I take the average of the averages, that will equal the true population mean. So again, there's some uncertainty involved, and we know that the larger the sample size, the more confident that I am that it's truly representative of the population. Now let's go back and review a little bit what we learned about the central limit theorem from previous chapters. If we know that the population has a particular distribution, and in this particular case we'll say the population is of x values, is normally distributed with some mean mu and standard deviation sigma, then the sampling distribution that we'll represent by x bar is distributed normal as well with the same mean, but the standard deviation changes. The standard deviation becomes smaller, and again, the larger my sample size, the smaller that standard deviation will be. So if you want to think about it like this, as n increases, this overall fraction decreases. So that's one scenario. Another scenario would be if my population is distributed with some shape that I'm not sure about. It's not normal, it could be skewed. So the question mark represents I'm not sure of the shape, but it has some mean and some standard deviation. The sampling distribution here I can talk about as being approximately normal if n is large enough. So for my sampling distribution, x bar is distributed approximately normal, same mean, same standard deviation, sigma over root n as before, and if this is n is large enough. Now remember, what did n mean large enough? Well, greater than or equal to 25 was one rule of thumb. If we had some slight skew and mild outliers, and another rule of thumb, of course, is 32. I think the book purports n greater than or equal to 25, so that will work for us. Now what we do is we take one random sample of size n from this population, and we rely on the known properties of this population to estimate the sampling distribution n. So that's what we're trying to do here. Now, when we take a sample and we look at one single value from that sample, that is called a parameter that I'm using to estimate with by a statistic. So let's go ahead and look at that. If we take a simple random sample and I look at a single value, it's called the point estimate. So a point estimate is a statistic that estimates a parameter. Now remember, a statistic is based on a sample, a parameter is based on a population. So a point estimate could be x bar is the point estimate of mu. Another thing that we could say here then is p hat, the sample proportion, is the point estimate of the population proportion, which is just p. We could also say S is the point estimate of sigma. The sample standard deviation is the point estimate of the population standard deviation. So again, this idea of a point estimate is very important, and it's good to know what the point estimates are and what the population value is that they're trying to estimate. So another good test question, fill in the blank type question. So what we do from here then is when we take a random sample, we can compute the sample mean and an interval of size plus or minus, let's say, 2 standard deviations about the mean. So this is kind of based on that 68, 95, 99, 7 rule. So based on that rule, we would think that about 95% of all intervals computed with this method would capture the true value of mu. So let's kind of back that up and write it all out. So based on the 68, 95, 99, 7 rule, I'm going to, out of this rule, use this middle value. So from here, what would happen is I would go 2 sigma from the mean. Now 2 sigma from the mean would mean I could add 2 sigma or I could subtract 2 sigma. So here would be the mean plus 2 sigma for my right endpoint, and then my left endpoint would be the mean minus 2 sigma. Now that's if we're only looking at a particular population value, but if I do this based on a sampling distribution, I need to remember that my standard deviation changes from sigma to sigma over root n. So these are if I'm working with x bar. Now I don't know mu anymore if I'm working with the sampling distribution, so I'm using x bar. And this is assuming sigma is known. So we're assuming sigma is known for this situation. And so what I'm coming up with then is some sort of an interval. Instead of just a single value, I'm coming up with an interval of values. So what I'm roughly coming up here is, instead of a point estimate, a single value to estimate a population parameter, what I'm doing is I'm coming up with this confidence interval, and we'll call it a confidence interval because of this 95% value, and an interval because it gives us a range of values. So let's go ahead and look at what a confidence interval is and look at some of the characteristics of a confidence interval. Now, a point estimate was a single value that estimates a population parameter. A confidence interval is a range of values that estimates a population parameter. And this is nice because it gives us some information about spread, about standard deviation, etc. Now, that's the first start for a confidence interval. Now, the general form of any confidence interval, and again, good test question here, is to start with a point estimate and then say plus or minus some margin of error. Now, this margin of error takes up 2 things. And you can see these are called the margins of error right here. The margins of error take into account some sort of spread or variability here with the sigma over root n, and then it takes into account some value that talks about confidence, and that's this value right here. So point estimate plus or minus margin of error. Now, a confidence interval is a range of values that have some sort of confidence level. Now, the confidence level that we looked up at here was 95%, but we can have all sorts of different confidence level. Now, this probability, this confidence level, basically quantifies the chance that an interval contains the unknown population parameter. So, you have to be careful about how you interpret a confidence interval. So let's look at a graph that will help determine how we should interpret a confidence interval. So the way that the interpretation of a confidence interval works is we are trying to estimate mu. we try to estimate mu with x bar. So each of these little dots down here represent x bar, and they are the point estimate of mu. So each of those little dots that I have filled in there are x bars, and you can see that we have a lot of those little dots. Now those little dots are also the midpoint of the confidence interval. Now this first confidence interval goes from this left endpoint to this right endpoint, and you can see that it does capture that true mean value. This second one captures the true mean, this third one, and the fourth one does too. But notice that this fifth one does not capture this true mean that's right here at mu. So what our hope is if we randomly select our values, over the long run about 95% of my intervals will capture that true mean, 5% won't. And what we do is we hope that the one we just built is one of the 95% that do capture the true mean. So that's kind of the general interpretation of a confidence interval. Now, of course, when we talk about a confidence interval, we need to remember that we have the point estimate, like we have down here, this midpoint, and then this piece right here is my margin of error. So that's adding the margin of error to the point estimate, because this black dot right here is my point estimate. It's the midpoint. And then of course I don't only add the margin of error, I subtract the margin of error to come up with my lower endpoint as well. So that's working with confidence intervals. And now once we have that general idea of what a confidence interval does, they're actually pretty easy to build. Now another thing that we can talk about with a confidence interval are some other general forms. I talked about point estimate plus or minus margin of error. A lot of times people will say center plus margin of error, but I think it's important to understand that this first value is the actual point estimate. Now the interval is made up of the point estimate plus the margin of error for my right endpoint, and the point estimate minus the margin of error for your left endpoint. So if you think about it, let's say we want to be 95% confident. I want to center this about the mean. So if I want to be 95% confident, 95% of my area is here. Here is my point estimate, and then both of these on either side, this particular distance from the point estimate to my right endpoint, point estimate to my left endpoint, again is the margin of error. Well, if I have 95% of my data centered about the mean, that means I have 5% of my data that's kind of out roaming around somewhere else. But because this is a symmetric curve, I can take and I can say, okay, my level of confidence, and we'll use C for confidence here, is 0.95. That means in the tails, what I have left for my tails is 1 minus my level of confidence divided by 2 because of symmetry. 1 minus my level of confidence divided by 2. So 1 minus 0.95 is 0.05 divided by 2 is 0.025. Now notice if I add up these three regions, I get 1 or 100% because 100% of my area should be considered underneath that curve. So that's kind of where we start with this. Now, I've talked about the 95% level of confidence, but I can have any level of confidence that we want. We can have 80%, 90%, 99%, but some typical values that we use are 90, 95, and 99% confidence. But if you want to be that confident, there's a price to pay for that. So we also have to talk about, okay, if I increase confidence, what else happens? So let's go ahead and look at the general form for the confidence interval for a normal population mean with sigma known. And we use CI to represent confidence interval. So these are our assumptions. A confidence interval for a normal population, and we're trying to build it for the mean, and we're assuming sigma is known. Now knowing sigma isn't all that realistic, but we'll look for other ways if we don't know sigma how to get around that. So again, we start with the same general form that we'll use for any confidence interval, and that's point estimate plus or minus margin of error. Now because we are trying to estimate the population mean, I use x bar right here is my point estimate for mu. So x bar plus or minus my margin of error. Well, the margin of error is made up of a couple different things. It's made up of some value that talks about confidence, and that's what we're going to call Z star, and then some measure of spread, our standard deviation, which is sigma over root n. Now again, sigma over root n is the standard deviation of the sampling distribution. And then C, or the Z star, talks about the level of confidence that we're going to be looking at. So for this general case, let's go ahead and look at an 80% confidence interval under these conditions. So what we do is we go ahead and sketch out our curve, and then grab your normal tables and your calculators. And what we want to do is we want to find 80% of the area centered about the mean. So this is 80%. Well, if 80% is centered about the mean, that means I have 20% to split between the two tails. So that would mean I'd have 0.10 in both tails. Now again, if you add up all three of these areas, you should get 100% or totaling 1 underneath the curve. Now this is the standard normal curve. So this is Z distributed normal 0, 1. So I should be able to grab my normal tables and then use my normal tables to find out what the Z star value is. So grab your normal tables, and what we want to do is we want to look up on our normal tables 0.1 on the negative side, or 0.8 plus 0.1 or 0.9 on the positive side. So I'll give you a second to look those up. Now let's go ahead and start by looking on the left-hand side, or the negative side of your normal tables. On the inside, the closest you can get to 0.10, let's see here, is a negative 1.28, and that value is 0.1003. So we'll go with the closest value. So that's a negative 1.28. So negative 1.28, and because of symmetry, I know this value up here is positive 1.28. Now again, because this is the standard normal distribution, this is centered at the mean. So for me to get started with this curve, then I'd have x bar plus or minus 1.28 sigma over square root of n. And to get started from here, I'd need to know my sample, and I'd need to know sigma and n to go any further. But we want to kind of focus on more about just levels of confidence. And you should be able to find those levels of confidence. It doesn't matter what's given, we should be able to look it up on our tables and use those values. And you always go with the closest that you can get. Now if you can't find the closest, what you do is you take the midpoint if it's exactly in between two values. Now there's some exceptions to this that I'll talk about when we get to them, but for the most part we should be able to, again, use our normal tables for everything. Okay, like I indicated before, there's some common levels of confidence that we look at, and you can find these for any levels of confidence. But I want to put down a few that are worth keeping in mind. So some common levels of confidence. We could talk about a 90% confidence level, a 95%, and a 99%. Well, we've already worked with the 95% a little bit, and remember we got 2 because we were using the empirical rule. Well, the exact value, if you set everything up, is actually plus or minus 1.96. For a 90% confidence level, it's plus or minus 1.645, and again, you can verify these on your tables. And for a 99%, it looks like you should go 2.575 because it's the midpoint, but actually the exact value is 2.576. So these are good to know. And again, you can use your tables to remind you and verify. The only one that you won't get correct on your tables is this one. Your tables would indicate more of 2.575 instead of 2.576. But you're safe using 575 or 576, but in Stats Portal they might want a little bit more accuracy, so it's good to keep in mind those values. Now, since we know how to build a confidence interval, what are some characteristics of a confidence interval? Well, first of all, I notice a couple things, and these are all good to know for a test. As confidence increases, and the arrow up means increases, what ends up happening is you notice up here I'm going from 90 to 95 to 99% confidence. Look at my Z values. As confidence increases, so does my Z value. So that tells me the width of the interval also increases. So again, as the width of the interval increases, that must mean that confidence must have increased as well. Because I can be 100% confident that I could guess how many patients we'll have today at the emergency room if I say somewhere between 0 and 1,000,000, but it's not very accurate. So again, a really wide confidence interval can be accurate but not very precise or useful. Now again, as confidence decreases, the width would decrease as well, so you need to know the vice versa of these. Now as our sample size increases, let's go ahead and look up here. As our sample size increases, what happens is this overall fraction decreases, which makes my margin of error get smaller, and that also tells us that the width would decrease as well. So as sample size increases, the confidence interval width decreases. And this makes sense because basically it's saying as I get more and more information, I can come up with a better and more accurate estimate. So those are some characteristics of confidence intervals. So now that we know about some of these characteristics of a confidence interval, let's go ahead and look at an example where we're building confidence intervals, and so we can see some of those characteristics in play. In this example, we're going to be looking at the density of bacteria in solution. Okay, and again, we're using the same assumptions as before. We're assuming that we know sigma. So we are looking at some bacteria in solution, and the measurement equipment that's trying to measure the amount of bacteria into solution has a normal distribution with a standard deviation of sigma equals 1 million bacteria per mil of fluid. So let's write that out. So again, I always think it's a good idea to kind of abbreviate this. So I'm going to use X to represent the number of bacteria. X is distributed normally, it says, normal distribution. The mean is not known, but I do know the sigma is equal to 1. Now what we're doing from here then is we are going to take 3 measurements. And based on these 3 measurements, the first measurement I get 24, so we'll call that X1, first measurement. X2 is 29, and X3 is 31 million bacteria per mil. Per milliliter. Okay, so now if you go ahead and calculate X bar would be 24 plus 29 plus 31 divided by 3. You would get 28. And again, this is million bacteria, million bacteria per mil. So now I start to build my confidence interval. Well, the general form for any confidence interval, we already know, is it's its point estimate plus or minus some margin of error. Now what we're trying to build is a confidence interval for the mean. So this is going to look like X bar plus or minus margin of error, which is Z star sigma over the square root of n. So let's go ahead and fill out what we know. For our example, we know X bar is 28, and we know sigma is equal to 1. We also know we took a sample of size 3. So that's the information that we have. Well, what I would like to do is I'd like to build 3 confidence intervals. I'd like to build a 90% confidence interval, a 95, and a 99. So for a 90% confidence interval, this would look like X bar plus or minus Z star sigma over root n. X bar is 28 plus or minus Z star, we'll fill that out in a second. Sigma is 1 over square root of n is the square root of 3. Now remember where Z star came in. 90% of the data is centered about the mean, which would mean I'd have 5% in either tail. So this was a value of 1.645. And again, these values I gave right up here. Again, worth memorizing, 1.645 for a 90% confidence interval with sigma known. Now to finish building this confidence interval, I go 28 plus or minus, and now I calculate the margin of error. So the margin of error is 1.645 times 1, which of course is just going to be 1.645, divided by the square root of 3. So for my margin of error here, I get 0.9497. So to find my confidence interval, what I do is I take 28 and subtract that value for my left endpoint, and I take 28 and add that value for my right endpoint. Now confidence intervals always go low to high, so I always start with the minus first. 28 minus 0.9497 is 27.0503 for my left endpoint, and my right endpoint is 28.9497. So what I can say here is I'm 90% confident that of all the confidence intervals that I could build of sample of size 3 from this population, 90% of them will capture the true mean, and I hope that this does capture the true mean. So you can't say I'm 90% confident the true mean is between 27 and almost 29 here, but what you can say is I'm 90% confident that this captures the true mean. Kind of a little bit different interpretation. Now let's go ahead and look at a 95% confidence interval. Same thing, x bar plus or minus z star sigma over root n, 28 plus or minus 1.96, 1 over the square root of 3, and again that 1.96 comes from our table that we have up there. You could also look it up on your normal tables. So my margin of error here would be 1.96 divided by the square root of 3. And for here I get 1.1316. Now let's look to see what happened here. Our margin of error, as my confidence increased, my margin of error increased as well. So that kind of worked like we thought. Now my left endpoint is going to be 28 minus 1.1316. So I get 26.8684. And then of course my right endpoint will be 29.1316. So there's a couple different things that we can look at here. As confidence increased, my margin of error increased, and so therefore the width of the interval increased. Now if you want to find the width of this interval, you would just subtract the right minus the left endpoint. Another thing that you could do is, based on this interval, could you find the midpoint? And the answer is yes, you can find the midpoint by adding together these two values and dividing by 2. Now let's see if we can predict what's going to happen for a 99% confidence interval. Still same form, x bar plus or minus z star sigma over root n, 28 plus or minus 2.576, 1 over the square root of 3. Now what ends up happening here is I can see that this value of z star has increased, so I would expect my margin of error to increase as well. So to find that margin of error, I have 2.576 divided by the square root of 3, and I get 1.4873. So I have 28 minus 1.4873, which gives me a left endpoint of 26.5127. Of course my right endpoint will be 29.4873. Okay, so let's see if we can fit these all on one screen. Margin of error, 90%, went from 0.9497 to 1.1316 to 1.4873. So as the confidence increased, you can see that the margin of error increased, and because the margin of error increased, so does the interval. Now just as a quick reminder, these are some values that you might want to memorize. They're going to be helpful to know these confidence levels. And again, you can always use your normal tables to kind of come up with them, but remember your normal tables will indicate more 2.575, which might put your calculations off a bit. So again, memorize these, make sure you know these. And if you're not sure about, gee, I don't think I can memorize them, remember you can use your normal tables and that will help you remember what they are. So that is how we build confidence intervals. Now another thing that we like to do with inference is we like to do tests of significance. And basically with a test of significance, I have a hypothesis, It's usually, numerical in this sense because we're running statistics on it. And then I perform a test of significance, trying to prove or disprove, either have evidence for or against this hypothesis. So confidence intervals and some tests of hypothesis actually have quite a bit in common. Let's go ahead and look at tests of significance. And these are two huge ideas in one chapter, so these are really important ideas. Now, what the deal is with tests of significance is that someone makes a claim about an unknown value of a population parameter. So it could be mu, it could be sigma, it could be the population proportion. There's lots of other ones as well. And then what we do is we check whether or not this claim makes sense in the light of the evidence that's been gathered. And this evidence is called the sample data. So a test of statistical significance tests a specific hypothesis using sample data to decide on the validity of the hypothesis. So I'm going to put all this into our lecture written form, and then we'll look at an example. So here's everything we just said. The things to remember here are, I'm trying to make a claim about a population parameter based on evidence, and this evidence is the sample data. And then what we're trying to do is we can't disprove a hypothesis, but we can say that it has support or it does not have support, or the evidence supports the alternative hypothesis. The only way we could have absolute proof is if we had some sort of a census. So let's go ahead and look at an example of how to set up one of these problems, or why we'd want to start one of these problems, and then we'll start talking about all the steps that are involved. Okay, for this example, again, this is kind of setting up why we would want to use hypothesis testing. Reminds me of the grocery store. You are in charge of quality control and sample randomly 4 packs of cherry tomatoes, and each of these have a label of 1/2 pound, which is 227 grams. And what we want to know is that label correct? Is our machine filling these tomato packages properly? Now the average weight of the boxes, so again, we have a sample of size 4 here. Their average weight is 222 grams. But it's advertised that it should be 227 grams. So what we want to start thinking of is we want to think, does this mean, is this enough evidence to say that I'm underfilling my boxes? Or did we just get some bad sample here? Well, if we collected more than 4 packs of cherry tomatoes, that might provide some more evidence. But that's the whole idea behind tests of significance. I want to figure out what's going on here. So is the somewhat smaller weight simply due to chance variation? Is it evidence that the packing machine that sorts cherry tomatoes into packs needs revision? Maybe that needs to add, another tomato per container, or maybe we need to have the scale recalibrated. So that's what tests of significance will help us do, is determine a solution to this type of a problem. Now when we start with tests of significance, the first thing that we do is we always state HO and HA, and those are called our null and our alternative hypothesis. So these are steps to significance testing. Now you'll see significance testing. Shouldn't talk and write at the same time. Significance testing, and you'll also see this called hypothesis testing. These are used interchangeably. Now the first step we always do is we state the null and alternative hypothesis. The null hypothesis is called H naught or HO. The alternative hypothesis is called HA, A for alternative. Now HO is kind of the standard. That's kind of everything that we know to be in place. So for our packaging for our tomatoes, our null hypothesis would be 227 grams. That's what we think it is. That's kind of what has been proven or shown or expected over time. The alternative hypothesis is basically going to be a general statement about what we are trying to disprove. So it's the researcher's hypothesis. Now we have to be careful here. These hypotheses, the null and the alternative, are mutually exclusive, meaning I can't have any overlap between them. So for our cherry example, what we would do is we would say HO, our population mean, is equal to 227 grams per package. Then our alternative would be, you know what, I don't think that's true. So one alternative that we could have are not equal to 227 grams, meaning I don't think it's filling properly. It might be too high, it might be too low, but I just don't think it's filling properly like it's saying. Now we could have other alternative hypotheses too. We could also have an alternative hypothesis that said mu is less than 227 grams. And we could also have an alternative hypothesis that says mu is greater than 227 grams. We just choose one of these alternatives. This is called the two-tail case because it has a right tail and a left tail. This is called a left tail hypothesis or a left tail alternative because it's less than, and this is called a right tail alternative in this case. Now, a couple of things to keep in mind. When you have a null and an alternative hypothesis, you always state these in terms of mu, and in general in terms of the population parameter. So always state parameters. Now notice they're mutually exclusive because here I have equal to 27, then I have not equal. There's no overlap between these cases. So the first step is going to state the null and the alternative hypothesis. Now we've already talked a little bit about the one-sided and the two-sided alternatives. We talked about the two-tail or the two-sided, the left tail and the right tail. Now what determines the choices of a one-sided versus two-sided test is the question we're asking and what we know about the problem before the test. So for instance, if I'm a consumer, I might think, you know what, I think they're underfilling these tomatoes, so I might want to check here to say I want to show that it's actually less than advertised. Now if we're the company and we want to make sure our profits are in line, we don't want to overfill the tomatoes, we don't want to give away more than what people are paying for, so I might want to test this case. Now the other alternative would be just, you know what, I don't know if my machine's working right, I don't know if it's under or overfilling, so I check the two-tail case. Now you need to know and set up the alternative before performing the test. You can't decide later on to switch it. Now we have to make sure we know before we start about the one-sided or two-sided because it will change the process that we go through to test the hypothesis. Now before we get to step 2, let's go ahead and look at some more examples of setting up our hypotheses. And usually you can tell from the context of a problem whether you should be using a right tail or a left tail test. So for our first example we have, is the active ingredient concentrated as stated on the label 325 milligrams per tablet. Now it doesn't say anything about less than or greater than or equal to or not equal to. So basically saying is the active ingredient concentration as stated on the label. So as stated on the label is equal to 325 versus the alternative hypothesis would be, it doesn't say less than or greater than, so we're just checking to see if it is as stated. So this is an example of a two-tail test. Let's go ahead and look at another example and see if we can set up HO and HA properly. So for our next example we have here is nicotine content greater than the written 1 milligram per cigarette on average. Okay, so we have a null and we have an alternative hypothesis. We're testing the mean. Okay, it's stated as 1 milligram. And what the researcher's hypothesis is it says, is it greater than as is written? So this is a right tail test. This is an upper tail test. Let's go ahead and look at another one. Now this one's not so obvious. It doesn't give a particular number here. So when we set up our null and alternative hypothesis, see if we can logic our way through this. First of all, it says, does a drug create a change in blood pressure on average? So we know we're checking the average. Now, it does not offer an explicit value for mu. What to write in the null and alternative hypothesis is implied in the question. We asked about a change in blood pressure. A change is anything that's not equal to 0. 0 would mean stay the same. So a change would be anything not equal to 0. So blood pressure remains the same. Blood pressure changes somehow, either increases or decreases, shows some sort of change. Let's go ahead and look at a last example. Now this last example provides quite a bit of information. It says, does a particular stream have an unhealthy mean oxygen content? Okay, so right away I know I'm testing the mean, so let's go ahead and get ready to set this up. Our null versus our alternative hypothesis. Okay, now they say an unhealthy mean oxygen content is a level below 5 milligrams per liter. Ecologists collect a liter of water from each of 45 random locations, so I have a sample size of 45, along a stream and measure the amount of dissolved oxygen in each, and they find a mean of 4.62 milligrams per liter. So this is what we have. We have X bar is 4.62, we have a sample size of 45, and then we have this 5 value up here. Well, that's the true population mean that I'm trying to test this against. Now remember, for a null and alternative hypothesis, you always use a parameter. Even though this is information that's provided, you're not using it to test for the null and the alternative hypothesis. This is the evidence for or against. Now, if we're looking for unhealthy levels, that would mean mu would be less than 5. So there's our null and our alternative hypothesis, and remember, we always use a parameter. Now again, this last one gave a little bit more information than is necessary. We never include sample results in the null and the alternative hypothesis. The next step that we want to look toward for our test of significance, or steps in the test of significance, is to talk about what a p-value is. Now a p-value is basically going to give you the amount of evidence that's provided with our sample values. So a p-value, the definition, is the probability if HO were true, or if H naught were true, of obtaining a sample statistic. So for our example 4.62 up here, as extreme as the one obtained, or more extreme in the direction of HA. And you're going to want to know this definition. It's going to help you understand what a p-value is. So again, this will be important to know. Okay, well, what does this mean? Well, what ends up happening is, with our tomato example, we randomly selected 4 boxes. The average was 222, and we want to see how likely it is to get that value of 222, assuming that the actual true mean is 227 as is stated. So let's go ahead and write that out. So here's kind of a summary of the values that we had. We had the packaging process is normally distributed with standard deviation sigma of 5. Now here's our null and our alternative hypothesis. We collected data, so here our sample size is 4 and our average was 222 grams. Now the question is, what is the probability of drawing a random sample such as we did, 222, or even more extreme if HO is true? So this right here is saying, what is the p-value? That's what it's asking you. Okay, well, the p-value is actually easy to find if we use a nice little picture. So let's go ahead and draw out the picture. We have 2 different distributions that we want to think about here. We have the distributions of our weights, and we also have the standard normal distribution that we'll want to talk about as well. So first of all, let's go ahead and look at the weights. Now from up here, weights are distributed normal, mean, I don't know, standard deviation is 5. Then what happens is I find the average weights, and they're distributed normal as well, mean, I don't know, standard deviation, I do know though, would be 5 over the square root of 4. Square root of 4 is 2, 5 divided by 2 is 2.5, so we could use either of these values. So my hypothesized weight is 227 grams. That's from here. Now what I want to do is I want to look at my alternative hypothesis, not equal to. So if I look at this, it says, what is the probability of drawing a random sample such as yours or even more extreme? Well, for the two-tail case, I can be more extreme in two directions. So I can be larger or smaller. So what I want to do is I want to plot the 2, 2, 2 over here, and I want to look at this as being as extreme or more extreme. So what we do then is we think as extreme or more extreme, and I'm looking for this value right here. So this is 1/2 of the p-value. Because this is a two-tailed test, I'll have to double that. So the way we're going to find this is we're going to standardize our score. Whoops. So when we standardize our score, we know the mean standardizes to 0. This value will standardize to 222 minus 227 divided by 5 over the square root of 4, 2.5. And what I get here is negative 2.0. So this says, what is the probability of getting a value as extreme or more extreme than 2 standard deviations below the mean? So to find half of this p-value, I look up negative 2 on my normal tables, and I get 0.0228. So that's half the p-value. Now the other half of the p-value has to do with symmetry. So the other half of the p-value is right up here, and this is because it's a two-tailed test. So half the p-value is up here, and because of symmetry, this has to be 2 standard deviations above. And if you wanted to look at the value here, if you look between 222 and 227, that's 5 units. If you look from 227 plus 5, that would be 232. So if you wanted to talk about this as 232 and standardize to a positive 2, you could. And I get 0.228 here as well. So my p-value is equal to 2 times 0.0228, or 0.0456. Now your book has some applets, so you can just put in the values and it tells you what your p-value is, but I think it's important to be able to use the tables so we kind of have an understanding for that. Now if this had been a single-tailed test, I would not have doubled the probability. I would have looked at either the left or the right depending on the alternative hypothesis, but this is my p-value. So what does this p-value mean? Let's go back to see the question it was answering. The probability is about 5% of drawing a random sample such as ours, or even more extreme if HO is true. So this provides evidence against HO because it's a fairly small p-value. So again, this is evidence against our null hypothesis. So you know what? This is kind of looking like, this is saying that our true mean might not be 227 grams. It might be actually less than that or different from that in this case because I have the two-tailed test. So I said it's fairly small, and that's kind of a relative way to talk because how do we say, what's small to you and what's large to you is different than what's small or large to me. So we need to be looking at how do we interpret a p-value. Now people will interpret these different ways depending on what evidence is provided, but basically when we're talking about interpreting a p-value, we're looking to determine whether random variation alone could account for the difference between what we expected to see and what we actually saw. So again, the difference between H0 and then the actual observations we got, was there evidence to support that or not support that? Now small p-values are strong evidence against the null, and we would reject HO in favor of HA. And we would say that the findings are statistically significant. So I would add a little bit more to this, and we reject HO in favor of HA. Large p-values, and again we haven't said what's large and small yet, large p-values don't give enough evidence against HO, and we fail to reject HO. Fail to reject. So a lot of times we say FTR HO. Fail to reject HO. We can never say prove. We can never say prove HA or prove HO. So if this gets a little bit confusing, think of it this way. When solving a crime, a person with a good alibi will no longer remain a suspect, but we have to look at the preponderance of evidence. But a person without an alibi is not necessarily the culprit, but they're just still a suspect. Likewise, we can reject HO if the sample data contradicts it, but failing to reject HO does not make it true. It just means we have evidence one way or the other, but we do not know the true state of nature. We can just provide evidence. So what about this large and small p-value bit? First of all, p-values are probabilities. And because they're probabilities, they range between 0 and 1 points inclusive. So p, instead of writing our probability notation, I'll just put the word p-value here. So p-value ranges from 0 to 1 points inclusive. You have to have the equal sign. Now the order of magnitude of the p-value matters more than its exact numerical value, meaning comparison-wise is more important than the actual value. So the book gives us a nice graphic to compare these against. So p-values that are close to 0, and the closer they are to 0, the more significant they are, and the further they are from 0, the less significant they are. But notice they don't give us a value here of 0.7 or 0.8 for comparison. We can just talk about here, the closer they are to 0, the more significant they are. Now we'll also have some comparison points that we'll talk about later on, but this is a good rule of thumb to remember here. The significance appears as they get closer and closer to 0. Now what we usually like to do is we like to have something to compare the p-value against. So what we like to do is we like to have this level of significance. So this would be the third step, is the level of significance. Now the level of significance we will call alpha. This is the Greek letter alpha. Now the significance level is the largest p-value that will be tolerated for rejecting HO. And this value is decided arbitrarily before conducting the test. So to summarize this, first of all, we have to state the level of significance before we conduct the test. We can't change the rules later on. We can't say, oh, let's play best 2 out of 3 and then you lose, and you say, oh, let's go for best 3 out of 5. You set the rules and you keep the rules in place. Now, if P is less than or equal to our level of significance, you reject HO in favor of HA. If your P is greater than your level of significance, we reject HO and we're done with the test. Now remember, when we reject HO, this means the test is statistically significant. So if you have statistically significant results, that means you rejected HO. So let's go ahead and look at this in terms of our cherry tomato example. So before we can get going here, again, let's follow through with our tests. Our null and alternative hypothesis, that's our first step. Now what we were testing against here was that mu equals 227 versus the alternative mu not equal to 227. So this is our two-tailed test. So again, first step, state HO and HA. The second step was to find our p-value. Our p-value that we found in our previous step was 0.0456. The third step that we want to go through is to compare this to the level of significance. And actually you should state the level of significance up in here somewhere, but we'll revise that, I think. Level of significance, which is 0.05. Now what we have here is we have our P is less than or equal to alpha. Therefore we should reject HO in favor of HA. Okay, so 0.0456 is less than or equal to alpha of 0.05. So I would reject HO in favor of HA, my alternative hypothesis. So I have evidence to support the alternative hypothesis. We have evidence to support that the true average is not 227 grams. So the results are statistically significant at the 5% level. So therefore the results are statistically significant at the 5% level. So that gives you your point of comparison. Well, what does this mean? This means the true average, actually what we want to do is we want to blame this on the data. The data supports the conclusion. And this is how you should always write one of these. Blame it on the data. The data supports or the data doesn't support. The data supports the conclusion that the true mean fill weight for tomato packages is not 227 grams. Now, and I'm not saying what it is, I'm just saying it's not 227 grams. So again, this is an example of how you can use tests of significance to draw a conclusion and to say whether your results are statistically significant or not. Now, this is kind of interesting because a lot in the news lately has been how certain car companies, I think maybe it was Kia, maybe another one, that were misrepresenting their mileage on their window stickers of their car, and the government was testing them and they weren't coming up with the same results. So another conclusion that we could draw here then is the machine is not filling properly, so the machine needs to be recalibrated. So again, these tests of significance are very important in real life for a lot of different things. For instance, a lot of things are automatically filled. You talk about, a bottle of cola. Does it exactly have 1 liter, or is it a little lower, a little higher? Well, on average, what would you expect to get? So again, tests of significance and hypothesis testing are very important, as are building confidence intervals. Now, you can also use confidence intervals to test hypotheses. So let's look at the steps involved in that. So CI again stands for confidence interval to test hypotheses. Now, we could do this for a one-sided test, but this works best for two-tailed tests. So again, we could use it for one-sided as well, but this works really good for two-tailed test. So I want to go through and still work with the tomatoes example. So tomato example. And for the tomato example, what we were looking at then was our null and our alternative hypothesis. This is the two-tail case. And I think I'm going to change up my directions here. We used to go p-value first, but I think we should state our level of significance next. And again, the level of significance is alpha. And in this particular case, alpha could be 1%, 2%, 10%, 5%. But for this case, I would like to use a value for alpha, let's say, of 5%. And then from here, what we can do then is find the p-value. And we found the p-value, and we took a sample of size 4, and we had the average of the sample of size 4 was x bar was 222, and our standard deviation, not from the sample but from the distribution that was given, was equal to 5. And then we found the p-value is equal to 0.0456, I believe. So this was our test of significance info. Now, what would we do with a confidence interval? So still the tomato example, but now I want to talk about a confidence interval. Now, because my significance level was 5%, I would like to build a 95% confidence interval for mu. Sigma known, sigma equal 5. And that's again from up here. So what we would do is the same thing as before. We'd have x bar plus or minus z star sigma over square root of n. So x bar in this case was the 222 plus or minus z star for 95% confidence interval is 1.96. Sigma is 5 over the square root of 4. So I have 222 as my point estimate. My margin of error is about 4.9 grams. So my confidence interval, my 95% confidence interval, would go 217.1 grams up to 226.9 grams. So, where's 227? Because that's what we're trying to check. Remember, mu equal 227. Is mu equal 227 in the interval? No, it isn't. Therefore, we would reject HO in favor of HA, and of course we already know what that means. That means the machine needs recalibrated. We have evidence to support the alternative hypothesis. So again, that's for a two-tailed case. We can also do single or just one-sided confidence intervals, but two-sided are a little bit more common. So this is the connection between the alternative hypothesis of being two-sided and a confidence interval. And notice we draw the same conclusions either way. Now there is a little bit different interpretation between a confidence interval and a test of significance. A confidence intervals quantify the uncertainty in an estimate of a population parameter. So we can come up with a range of potential values. A test of significance basically evaluates a statistical claim and then tries to determine whether it's reasonable or not. So those are a couple short or small differences between the two. Now to end up, we're going to do one last example, and this last example, instead of working on this two-tailed test that we've been looking at so often, we're going to be looking at a single-tail test. So let's go ahead and look at another example of a test of significance. And for this example, we're going to be looking at birth weights. So we're looking at the national average of birth weight for babies is 120 ounces. So if you wanted to look at the birth weight of a baby, you could say X is distributed normal, mean of 120 with a standard deviation of 24 ounces. Then what we do is we look at a subset of that, and we take a simple random sample of 100 poor mothers, and then we looked at the average birth weight of poor mothers. So the average birth weight here was 115 ounces. Now what we're looking at then is the comparison of 115 ounces to 120, and we can see that it is lower, but we want to know, is it statistically lower than the national average at a 5% level of significance? So that's kind of the setup here. So first of all, let's go ahead and state our HO and HA. Now our HO and HA, remember, are always parameters. So we're saying the mean is 120. We think that we might have something that's statistically lower, so we want to test the average for this group and test it against the mean and call it less than 120. The next thing that we'll do is we'll state the level of significance. And for us, the level of significance was given as 5%, so alpha equal 0.05. And the next thing we'll do is we'll calculate the p-value. Now when we calculate the p-value, basically we use that same standardization. You use 115 x bar minus mu naught. I'll write it out in general first. So x bar minus mu naught sigma over the square root of n. So for us that would be 115 minus 120 divided by sigma. Now if we scroll up here real quick, sigma was 24 divided by the square root of 100. Now if you calculate that, it should just be 100 there. If you calculate that, let's see what we get a negative 2.083. So that means I'm a little more than 2 standard deviations below the mean. So let's go ahead and write out what this looks like. Now the p-value always follows the direction of the alternative hypothesis. So x was the birth weight of babies, x bar is the average birth weight, and we're testing it against the alternative hypothesis, but we always assume HO is true. So we test this against 120. We have 115. And when we know if we switch this to our standardized values, that this standardizes to 0 and this standardized to negative 2.083. Now the p-value here is going to be a little bit different. The p-value is going to go in the direction of the alternative hypothesis, so I go less than. So this is the entire p-value. It's not half, it's the entire p-value. So the p-value here would be phi of negative 2.08, because remember I can only go to hundredths. So if you grab your normal tables and look up negative 2.08, I get 0.0188. So my p-value is 0.0188. So p-value equals 0.0188. That's a pretty small p-value. So let's look to see what happens next then. We have to draw some sort of a conclusion, so that's our next step. So make a decision. Now the only two decisions I can make are to reject HO in favor of HA. And I do that if P is less than or equal to alpha. Or I fail to reject HO, and I do this if P is greater than alpha. Well, for our situation, we have 0.0188 is less than or equal to 0.05. So we have this situation. So what should we do? We should reject HO in favor of HA. So there's your decision, and then we need to write out our conclusion. Now the conclusion should always be stated in terms of the alternative hypothesis. But we never say HO and HA. We try and write this out in layman's terms. So basically we're saying the data supports the conclusion, that the average birth weight of babies born to poor mothers is less than 120 ounces. So that's our conclusion. And I guess we should probably say something about the level of significance. So let's include that. So the data supports the conclusion that the average birth weight of babies born to poor mothers is less than 120 ounces at the 5% level of significance. So there's our conclusion. So we can see that everything that we do here follows a series of steps and a series of procedures. So the important thing here is to remember the steps and then include them as well. Now we could also talk about confidence levels here and confidence intervals, but again this would be a one-sided confidence interval, which isn't so common to work with. We're going to be doing this same procedure, these same steps over and over and over again for different population parameters for the rest of the semester, so it's so important that we get this down solid right now. Good luck, and remember, keep track of the steps and you should be fine.